All right, so today we're going to be going over some of the new material for the finals. So we're going to be starting with the lecture on the lecture from April 20th. And I guess first we're starting out with enols and enolates, ketones, stuff like that. So just to review about your carbons, it's important to keep in mind your alpha, your beta, your gamma positions. And so something about this is that you can have like you can use your you can use alpha beta, you can use Greek letters in your nomenclature. So this isn't strictly IUPAC because IUPAC uses numbers, but you can use it for these kinds of things. And so in this molecule right here, this is too thin. In this molecule right here, it's an aldehyde, but then it has a Cl, and the Cl is in the alpha position to the aldehyde. So then you can just name it alpha chloro. Wait, what? Chlorovaloraldehyde. Where does the val come from? I'm curious. Hmm. Um, okay, I guess we'll see that in a second. But anyways, um, so apparently the alpha carbon tends to be acidic, which is going to be really important for doing our reactions from here on. So we already learned about how to transform between a keto and an aldehyde and an enol, right? And so an enol is just when you have a double bond with an OH on it, and the ketone is when it goes back to being this, right? So that's the difference. You can think of it like this double bond goes up. But really what's happening is that the what do you call it? There's a hydrogen here that is being eliminated. So it gets taken off because it's acidic because in the alpha position, and then that creates the double bond when there's a carbocation there. But if you look into the acidity of both of them, the acidity of having just a second. I think I draw like a better molecule for a second there. Okay. So in this case, so in reactions, you always want to go to the side that's the least acidic. And the least acidic is actually this one. Okay. And this one is more acidic. Just that the alpha hydrogen can be lost kind of spontaneously through being a little bit more acidic than if it wasn't alpha to a carbonyl. So again, so the reactions tend to favor the ketone a lot more than they favor the enol, right? And we know this because every time we do a reaction, we pretty much don't show the enol outcome. The ketone outcome is the most important one because it is the majority of what ends up happening. Um, so yeah, so you'll only find the enol in small amounts, and you'll find the ketone much more frequently because it is less acidic. All right. So the only exception to this is in the situation where we have this right here, and actually this one prefers it much more prefers to have one of them as an enol and one of them as a ketone. And this is because there is a possible hydrogen bonding between this hydrogen right here and this oxygen right here, right? And so that's why, even though in general we prefer to keep things in the ketone position, if it's double like this, you want one of them ketone and one of them enol, and that'll create a more because of the hydrogen bonding. So that question will probably come up. All right, so let's work on some reactions now. So these reactions from now on are going to be dealing a lot with these different kinds of carbonyls in with aldehydes and alcohols and stuff like that, which we've already touched on a little bit. I mean, you can think of this whole like semester as having been about carbonyls in a way. I mean, we started off with Grignard and we've never really let go of it since then, right? So these reactions are not much different. So first we'll have our aldol reaction. And so for our aldol reaction, you're going to be using you're going to be creating an aldehyde and an alcohol. So first you have, for example, an aldehyde right here, and it's reacting with another aldehyde. So what happens is that the acidic, so this one has a hydrogen right here, right? And this is an acidic alpha hydrogen. So this one is going to be, it's not going to protonate spontaneously like that arrow would suggest, but it is likely to be given up by something else in the reaction. Oh, by the way, what it's reacting with is KOH and H2O. And so that KOH is the base that will take away that hydrogen, right? So once the hydrogen is gone, so I'll just draw an OH attacking it because that's more accurate. So once the hydrogen is gone, what we have is we have a negative charge in this position, right? And a negative charge just means a lone pair. So I'll denote that like that, okay? And so what happens is that this lone pair or negative charge, whatever you want to think about it, is going to attack the carbonyl. And then this is going to be forced to go up to maintain octet, right? So what does that give us? That gives us this. That one stays a carbonyl, and then it's attached to, this is just going to be really odd looking. Okay, it's attached to this. All right. Oh, wait, no, these are supposed to be aldehydes. Okay, there. So, yeah. All right. Can you guys hear a weird sound or no? I'm just wondering because I can hear this like little like.
No.
Okay. All right, cool. Yeah. It's not bothering me, but I was just wondering about you guys. Okay. So yeah, so this is what it's going to produce essentially. And from there, it could kind of like switch back and forth, or actually no, like let me read all this. So 1, 2, 3, 4. Okay. So 2 has OH, and then 4 has a carbonyl, an aldehyde. Yeah, so this is what we end up getting. Now, we started off with the same reactant, both of them, so that's why it's kind of like symmetrical. It doesn't really matter which side you draw which one on, right? And then with heat, though, what can happen is that, oh, this is the same thing, by the way. So with heat, what can happen is that this can be protonated and can form a double bond through elimination. So what that ends up looking like is you just completely remove the OH, and then you put a double bond in its place. And of course, the double bond is going to follow your regular Zaitsev's rules. So we prefer for it to go to this position instead of this position. That's aldol. Okay, so aldol involves what? 2 aldehydes, and then you can either end up with aldehyde and alcohol or an aldehyde and a double bond, whichever one you prefer. Now for glycine, you actually end up with a beta keto ester, which is why it's so helpful because as we know, there's so many helpful things you can do with a beta keto acid. So for glycine condensation, we're going to take esters, right? We're going to take esters, and we're going to take 2 of them. And this is going to react to a very specific list of things. So Na and then O, CH2, CH3. So any base, essentially any strong base, right? will do. And then also, then an acid, secondly, has to be used. So what's the base going to do? The base is going to come along with strong base, and it is going to attack the alpha hydrogen. And so it's very much a similar process. What's going to happen from this point is that we now have a negative charge here. And this negative charge can do the exact same thing, just attack one. So like literally like the same thing. But in this position, this will come up, come down, and that will break off, right? So that's the difference between using an ester and using an aldehyde. So from here, when you form it all together, what you get is you get this. And let me just straighten that out. So 1, 2, 3, 4, 5, and 6. So 6 members. And then I just need to make sure these are all correct. Okay. So this is what we end up with. And this is a beta keto acid. So that's how to get that one. So again, aldol uses 2 aldehydes, glycine uses 2 esters, and you get totally different end results. So you just need to look at your end result and then figure out which one you want to use, okay? Okay, alpha substitution. So for alpha substitution, it's exactly going back to Orgo 1, where we learned about different kinds of substitution. And what is substitution? You take something, remove it from a molecule, and then put something else in its place, right? Fortunately, since these alpha hydrogens are so acidic, they actually make a great tool for protonating and then creating a negative charge so that you can attack something, right? So that's really cool. So all we have to do is, the example he gave here is carbonyl, and it's reacting with NaH. And so NaH is just an H minus, which is also a base, right? Because it wants to become H2. So it'll take one of the alpha hydrogens, either side will do, right? We have 4 hydrogens to choose from. And so it'll simply take one of the hydrogens, remove it, and make it into negative charge. Now, the second thing that we're reacting this with is also this thing right here. And so, again, all we're doing is we are going to remove a hydrogen, so that gives us this negative charge. And then that negative charge will come and it will attack because the bromine will protonate just spontaneously, like we've learned so long. Like every time, like we just know that like bromines are very likely to protonate on their own because they're pretty good leaving groups. So negative charge will attack that carbon. So what we get is actually maybe I'll draw it the other way. So we get this part that had the bromine on it, and instead it's going to be attached to the pentane with the carbonyl on it. So this is what our product will look like. So this is how to use those acidic alpha hydrogens to your advantage to do substitution, right? Okay. So then it looks like after that, he goes on to talk about the exact like ways that you can tell what's more acidic, what's not. Because as you can imagine, he could give you a question on the final that has like a whole bunch of these kind of questions, and they all have alpha hydrogens. And then he asks you which one is going to react with this product fastest. So you just need to figure out which one is the most acidic. And so in terms of lining them up in terms of acidity, so it looks like the most acidic is one that has 2 carbonyls on it. And you can think about it like the alpha hydrogen here is actually alpha to 2 carbonyls. So that just makes it more acidic in general as compared to if it was just alpha to 1 carbonyl, right? And then next you have your Next, you have a carbonyl that has an alpha hydrogen here that like it doesn't really matter what's on the other side of it, but anyways, the important part here is that it just continues to be R versus one where it is an ester, right? So being an alpha hydrogen to an ester is less acidic than being an alpha hydrogen to a ketone, right? The ketone and this is ester. So so this would be the most acidic, and this would be the least acidic. So again, the most favorable is to be obviously alpha to more carbonyls. The more carbonyls, the better. And then the second least, then between other ones that are only adjacent to one carbonyl each, it's more favorable to be next to a ketone versus an ester in terms of acidity, right? So we would say that this one would react the fastest, this one would react the second fastest, and this would react the slowest. Okay, LDA. So I'm not sure if you guys have seen LDA before, but it's actually not too difficult. So LDA is, I believe, a hindered base essentially. And so, oops, yeah. So here's a reaction with LDA. So LDA and then THF or any of those solvents, and then some kind of substitution, something that we'll be substituting. So all that LDA does is it's going to change this so that the alpha, it's basically going to remove like an alpha hydrogen, and that alpha hydrogen can then attack your substituting group, right? So this will come off somehow. We'll end up with this and a negative charge here. The negative charge, all it has to do is attack this, this right here, right? Because the I, oh, that's an H. The I will protonate spontaneously. So what we end up getting is this. 1, 2, 3. All right. So yeah. And then again, so like you can use LDA with any kind of carbonyl. It does not necessarily need to be an ester. So you could just use it with a regular carbonyl. And then what will happen is that the alpha hydrogen will be protonated, and it'll attack. And then let's say that we're going to use, in this case, I don't know, something like this. So, so all that's going to happen is that we're going to get this. So it's just another form of substitution, really. And then, so then here he's also showing, so this is on page 3. He's also showing that it doesn't necessarily even need to be like this kind of good leaving group, which is kind of, you should be pretty familiar with that idea anyways. So let's do the exact same example as above, but in this case, you can use LDA, TH, whatever. But then when it comes to the bottom part, you can actually just have like something with an OH, but then you need to remember to include H3O plus because H3O plus can protonate an OH, right? It turns the OH into water, and then water is a good leaving group. So it's really regardless. Just make sure there's a good leaving group. Make sure that there's a carbonyl, and you're good to go. Do you guys have any questions so far?
No.
Okay, cool. And then let me see. Okay, so we talked about aldol condensations. Um, we've really gone over most of this stuff. This stuff isn't too bad, right? So I guess here's an intermolecular one that we use to practice. So this is an intermolecular aldol condensation. So what he's got here, it's a little bit complicated. Okay, so there's a carbonyl in this position and a carbonyl in this position. And so when you're reacting this with a base, so so here you wrote Na2CO3 and H2O heat. He said it's equivalent to an OH minus. So I guess that's just a base, really. And so what a base would do is it would take away one of the alpha hydrogens, and then that alpha hydrogen would attack the carbonyl of another one. So I don't really know. There's lots of different alpha hydrogens you could use, but I think they would all pretty much produce the same thing. So let's just take, he took this one, turned this into the one that's a negative charge, and that'll just attack that carbonyl. That carbonyl will be forced into an OH, right? So all I have to do to count up and figure out, like, okay, what does my shape look like? So I'm going to figure out how many members there are in this ring, right? That's 7 members in that one ring. So it's not, easy because like we're not used to doing this a lot. But okay, 7. So it's a 7-membered ring, and it has a carbonyl at the top. As for the other one, I'm gonna go ahead and erase all these numbers. You can, as for the other one, I'm just gonna go and do the same thing to figure out how many members there are, and it turns out that there are 5. So draw that a 5-membered ring. Now the OH is in this position. The OH could stay like this, or with the use of heat, like we talked about, it would further become this. Okay, so it's just the aldol condensation that we've already talked about lots of different times. And something that he pointed out here is that if you have a mixed aldol, and especially if there's multiple different kinds of alpha hydrogens, it could end up being a complete mess. So you do want to watch out for that. You want to avoid a situation where there's multiple alpha hydrogens. And so the example he gives is this. So think about it. In this situation, you could either develop a negatively charged carbon in any of these positions, right? And from there, they could react with the carbonyls, and you would end up with so many different products because each one of these hydrogens is different. So that would never ever do. So watch out for that one. So going back to Claisen condensations, so just to review, a Claisen condensation is one that involved an ester. It involved an ester instead of just aldehydes or ketones, and it creates beta keto acids. So those are the 2 hallmarks of Claisen condensations. And so I guess he's trying to show you like a little trick here. So for this little trick, so here's a problem. So just like we talked about, we're including a strong base so that it can create that negatively charged alpha carbon, so it can remove that alpha hydrogen. And so once we have a negative removed alpha hydrogen, and again, like these are really clean and smart because there's only one alpha hydrogen. And so that alpha hydrogen is going to attack another one of the same exact molecule. So it'll come here and attack here. That'll break off the O. So what we're going to end up with is just redraw the exact same thing from the start and then attach the carbonyl on. Okay. So once you've done this, it'll be interesting to learn that all you have to do, like in order to visualize this, you don't have to draw it out every single time. All you have to do to visualize it is that just take the start, and then if you can cut it off right before the ester portion starts, that is the only part that you just need to add on to this right here. So there's no need to really go through, like, drawing everything out. You'll notice a pattern, which is that you just cut it off from the oxygen, and that's the part that gets inserted there. And why is this helpful? Because if sometimes he'll ask you a question where he'll give it to you the other way around. So let's say that he gave us this. So if he gives us this, sorry, if he gives us this, what we kind of have to do is we have to figure out, okay, well, what did this come from initially, right? And so I'm just gonna have to go and I'm gonna have to figure out, okay, so this was all part of the one side that did end up keeping its oxygen, right? So this must have been where its alpha hydrogen was. So that means it cut off right here, which means that this is the only other portion that was left from the other side. And that actually works out perfectly because then it makes a lot of sense that our starting products were both this, two of them. And if you're confused by that, just go back and think about that problem, and think about like any way that makes sense in your head to break it up if you got like a backwards kind of problem for this. Okay. So then there's a Dickman reaction, which is something we haven't talked about. It's actually just a intermolecular Claisen condensation though. And so it's honestly not even that hard still. The example he's giving here in the lecture shows that we have this. And so we just need to assume that one of these alpha hydrogens, it could be this one, or it could be this one, and it really doesn't matter because this is a symmetrical molecule. Either one of them is going to attack the other carbonyl. And so this one is a little bit more complicated because it's a little bit difficult, especially when you compare it to like aldol condensations that are intermolecular. This is going to be a little bit more tough. So I think the first thing that I would do is I would count some of the carbons. So I would count the positions where the two carbonyls are. So I'm seeing that there's 6 carbons between where the two carbonyls are. So I'm going to draw like a rough, like 6-sided shape, but it does have to be open, right? So we have 1, 2, 3, 4, 5, and 6. Now, I know that at 1, there's a carbonyl, and at 6, there's a carbonyl. And they each have the same exact structure coming off of them. So after that, you can just, again, take this one hydrogen, and I don't want to, do all that because you guys know exactly what happens, but just change this to a negative charge, and then I'll make this attack there. So once I've attacked there, I'm going to erase all these numbers again so you can see. Once I've attacked there, you just have to figure out how many members there are in the circle. And so that's going to be 1, 2, 3, 4, 5, and that's it for the circle. So using that information, I can just go ahead and draw my molecule. And I know that I'm just going to put, because like it'll maintain the same orientation, I'll put my no, that's not the carbonyl that gets maintained. I'll put my OH here with the, and then, so it's, oh, shoot, no. I completely messed up. That's not an aldol condensation. This should remain like this because broke off here, right? That's an important step that I was kind of forgot for a second. So then this is kind of what you end up with. And then, yeah, and so this is your answer. This is a beta keto acid. Oh, wait. No, it's not. Something is wrong. Yes, something is wrong. Okay. Yeah, so again, that's a very useful piece of information you can use to figure out if you did it correctly, right? Is it a beta keto acid? I was like, no, that's not a beta keto acid. So this is actually the correct structure. I'd forgotten about that. So this is a beta ketone acid. You have your alpha carbon and then you have your beta carbon. Here's your acid, obviously. There is a ketone on the beta carbon, so it is the correct answer for this problem. And then obviously you can also do some mixed Claisen condensations. Just remember though, you don't want to have too many options for your beta hydrogens because that's what creates a mess, okay? All right. So we can actually, we've talked about, adding different kinds of alkyl groups to the alpha position from a carbonyl. And so this is kind of just back to what we already discussed, just another example. Here is a very acidic alpha hydrogen, right? Because it's actually positioned between two carbonyls, which makes it pretty advantageous. And so this is just going to react with, again, something with a good leaving group. And then it's showing here K2CO3. This is the second time we've seen this as being equal to an OH, right? An OH minus. So whenever you see, so K2CO3 is a base essentially, and so that's just going to aid in taking that alpha hydrogen. I'm not quite sure, but maybe it's better at targeting your alpha hydrogens than some other bases. But either way, you can either use this or you can use KOH or NaH even. Those were all the options we've seen. But the only reason I'm pointing this out is I would probably not use this in my retrosynthesis because, like, why? But you just need to know it for the questions on the actual exam. And so when these two react together, it's just what we already talked about, right? A way of adding alkyl groups to the alpha position. So that's what we end up getting, right? And so this is going to be really, really important for your retrosynthesis if you see like an alkyl group that's been added to what you started out with. So if I started off with something like this, if I start off with like this and then I end up with something like this, I don't know, something like that, I would know that maybe like a, yeah. So I would know in this case that this probably somehow got turned into a ketone, and then there was an addition of an alkyl addition to the alpha position, right? So that's kind of the stuff we're going to have to learn how to do before the final. Okay. Wow, this lecture is long. Okay. Now he has an ester synthesis as well. I'm just looking at this to see if it's important. Oh yeah, okay. So he uses basic hydrolysis here, which is going to be really interesting for removing your acid completely. So that seemed like a really important thing to go over. This is page 6 again. So he starts off with this molecule. There's 2 of them. It's undergoing the basic process we know of a Clemmensen reduction. And so, there's no need to draw that out, but I'll just write, wait, am I saying Clemmensen? Is that the right word? I think it's Claisen. Clemmensen is completely different. Clemmensen is completely different. We know Clemmensen. This is Claisen. So it's going to undergo a Claisen condensation, and then there's no need to draw that out. After that, it will they will hydrolyze the so actually let me just draw the product. I'm just not going to go through how it's done. So this is a product. And so you see this is at this position it has an ester still here. And so what we're going to have to do is turn that into an acid, and that is done with KOH, H2O. It looks like this is just heat. and then H3O plus. And so what that does is it just clips that off and you're left with this. Oh, also here's an example where it doesn't need to be necessarily a beta keto acid. This is a beta keto ester. You know what I mean? Um, so what happened is that we did maintain an ester right here. So this is a beta keto ester, right? Whereas in this one above, oh, this was also a beta keto ester. Yeah. So it's not like you obviously have to have a beta keto acid every time. It really just depends. But look for, a beta keto ester or a beta keto acid. So this is all this is going to do is remove the ester part and change it to an acid. From there, you just have to use heat to actually take away the acid completely. So I believe this might be new for you guys. I'm not sure, but it does seem like quite a jump to simply use heat to remove an entire acid. But it does make your life easier, right? When you're doing your retrosynthesis to make such huge steps in terms of synthesis with just simple things, right? But where it is tough is in the questions that you get on your final. When he shows this with heat, you might get a little bit confused and just wonder what you're supposed to do. I just always like to reduce things. If I see like something like a base like heat or something like that, just keep on reducing it, or hydrolyzing it. Um, okay. So I'm not seeing too much more that we really need to talk about. Um, yeah. It's all the same kind of stuff. So here's one thing I will point out for your references, which I'm noticing from the problems he's giving, or like the way he's presenting the material in the lecture, and I think this is going to come up on the final. When you're doing a retrosynthesis, right? Sometimes you're going to have a combination of things. First of all, you're going to want to so let's say that we have this starting product right here. Okay, so if we have this starting product and we want to get to something that is like this, we notice is that these are two alpha groups that must have been completely added on, okay? And so, because it's definitely not like, yeah, anyways. So what's going to happen is that you notice that there's two, one and two, and these are added on. They're alkyls that are added on, and they're added to an alpha hydrogen position. So that tells us this is just alpha addition of an alkyl group, but it happened twice. So what you want to do is before you start cleaving off all of this, go ahead and insert those other things, right? So that would be like NaO, no, NA, yeah, NaOCH2, CH3, like a base of some sort, and then your different alkyl groups. So the first one will probably look like this, and then I'm just going to repeat the second step without drawing the intermediate, but NaOCH2, CH3, and then the second one would have 1, 2, 3, 4. Okay. So you're basically adding those two things on at once before you go ahead and cleave off this portion right here, because it's much more advantageous to be adding them while it's a beta hydrogen to two different ketones, right? Do you guys get that? Am I making myself clear?
Yes.
Okay, perfect. So this reminds you probably a lot of exam one. in exam 1, we had to pay attention to what's more favorable, do that step first, and then cleave things or whatever, change things around. Okay. So I'm just saying a reminder here that the ketone is the more stable form than the enol, right? And that's going to be like enols are very, very uncommon. They're usually just there for a second before it quickly transfers. So just keep that in mind. Okay, so now that we've talked about adding alkyl groups to an alpha position, we're going to talk about alpha halogenation, which is totally possible as well. So it's a little similar. All you have to do is it's it's actually pretty easy. But here's an example that he gives. So here's an aldehyde, and all you do is react it with Br2 and H2O, and that literally inserts a Br right there to the alpha position. So that's alpha halogenation for you. All right. What else? I'm not really understanding all these other notes that he put there, but I think he's trying to explain. Honestly, I don't really know. But yes. Oh, okay. So then there's a mechanism for that. Mechanism for alpha halogenation of aldehydes and ketones. Looks like we need to know that for the exam. So um, I guess I'll go ahead and try to walk through it a little bit. So for the mechanism, what it looks like is that the ketone is actually going to, let's just use the example we had above, because that's different than the one on the paper, so you can practice it. So it looks like this will simply, become, so it's much more likely to go this way, but it will also a little bit become an enol. And so we just take the enol form, an OH here, hydrogen there, and the double bond is now here. And so all we're going to do is, from this point, when you add your two BRs, you're adding two BRs, right? The double bond is going to grab one of the BRs and take it on to the, it's going to follow, wait. It's not like Markovnikov or anti-Markovnikov, but it's going to go to the position here. This one right here. And that leaves what? It leaves a positive charge here. And then from there, the OH has to kind of fulfill that. So it's all from the OH on this point, because if you see like what we're doing here, it's just about reinstating that carbonyl. So that's an OH at the moment, right? And so what happens is that a lone pair from here is going to come down to create that double bond that is our ketone or our aldehyde. So that creates a double bond here. But the O still has an H attached to it, so we just need to really specify how that H gets taken away. And it'll get taken away from a second BR. So the second BR will just come take that hydrogen, and then, one pair will be allowed to go onto itself. That gives us and then also there is an HBr as a byproduct because it is from this step. I'll show it in red. This step right here yields us the HBr here. Yeah, and then there should be nothing else in terms of byproducts. All right, so that's a mechanism that apparently you need to know. Oh, yeah, something else interesting. So if you have a chiral carbon for your alpha carbon, when you make it racemic, it will become achiral. Or sorry, when you make it into an enol, it will become achiral, but it will be racemic, which is the important part. So if he asks you for stereochemistry, here's a question. And in this question, we see that there is an OH and then a hydrogen, right? So this is clearly chiral. And just to remind you of chirality, sorry. To remind you of chirality, chiral carbon is a carbon that has 4 substituents off of it. Each of those substituents must be unique from each other. And in this case, you see that that is the case. Also, yeah, that's it actually. That's mainly the way to summarize it. And so when you do this, and obviously like this is a more favorite product, but for the less favorite product, which is the enol, we have a double bond here and OH here. And then also an OH here. So it says that in this case it's going to be achiral and racemic. So we're going to have to make sure that we wait a second. Can't you only do SNR for chiral carbons? That doesn't make sense that it's achiral and racemic. I'm actually not completely sure about this one now. Do you guys see what I'm talking about? Or no, I'm confused. Okay, I don't really know what he means by achiral and racemic, because let me just look up. I mean, racemic. I thought racemic meant. I'm just gonna look up if this is a thing. I might be confusing myself, to be honest, because I was never such a huge fan of yeah, so this is, yeah, you can't have something that's achiral and racemic. So I think what he might have meant by this is that it's achiral and then it will become racemic when it goes this way. So my guess is that if he gave you an enol like this and asked you for stereochemistry, then you would have to give him 2 products, right? Because this is achiral. So you'd have to give him one that looks like this, and the OH is up, and the H is down, or you'd have to give him the other one, which is where the OH is down, and the OH is down, and the H is up. Just make sure that there's an NR there. This isn't the only ways you can do it. So that's my guess. I think that's what he's trying to say there, that when you go from an enol to a ketone, there's no real way to know what it originally looked like. So you have to there's going to be a mix. You have to give both of them. And I think that makes a lot of sense too. Okay. And you can use an acid to catalyze something becoming to favor an enol product. And so that might be a mechanism that somehow comes up, a small mechanism, but a mechanism nevertheless. So this one is where you start off with a ketone, and then you're reacting this with H3 plus, so because that's acid catalyzed. The O from here is going to grab a hydrogen. This is our regular starting thing. Then at that point we have this. And then also at this position, we have an acid that is going to be, or sorry, an acidic alpha hydrogen that's going to be taken. This is going to go here. And then this is also going to accommodate the plus charge. So then what you get is you get the double bond here, and this is now an OH. Okay, so that's the final product, an enol. So acid catalyzed enols, ketones to enols. Okay, and this is surprisingly long because isn't this lecture? There's two lectures for the same lecture, like two sets of notes for the same lecture. Although the second set of notes is more like drawings with different kinds of reactions and stuff to practice from, and it includes the review questions. So if anyone has any questions about the review questions, let me know. I won't really go through them specifically. If you have any, you have to do them on your own and then bring them to me. When it comes to the material for the final, I'll just remind you, you don't have too much to work off of. You're not going to be given any exam questions that have the final stuff material on it. So, and this is a big portion of the exam, so don't, kind of forget about it. The only way to really prep for the final material is to, number one, use your two quizzes, which aren't as helpful because they're only focused on a small amount of material. And then also every single review question he's ever given, every single retrosynthesis, every single NMR that has to do with this new unit will be really, really important because it's your only resources. You can also go through the homework problems if you want, but like, I don't think there's any need really. Just, you probably have enough to focus on with just all the questions he gave you in class. Okay, so this is a Hell's reaction. So a Hell's reaction is just gonna add a an alpha halogen, but to an acid, a carboxylic acid. So we've already added an alpha hydrogen to a carbonyl, but in this case, okay. So in this case, we have a carboxylic acid instead, and we're trying to add an alpha halogen. So all we have to do is, in the last one we did Br2 and let me see, H2O, right? We did. So this one's obviously just an aldehyde. But if you want to add it to an acid, you're going to do Br2 and PCl3. Don't confuse this with like P. I mean, sometimes when we do, because we've done Br2 and PBr3, we're adding to a ring for that. So this is a little bit complicated. PCl3 will add it for an acid to the alpha. So just the exact same thing as here. And all we do is add the Br there. And then he's showing that you don't even need to write PCl3. You can just write P apparently. And it just does the exact same thing. From here though, this is where things get interesting. Once we've added our BR, we can actually use this BR to do some cool things. So the first thing we can do is we can change that BR into an OH. And how we do that is K2CO3, which we've seen before. And K2CO3 is essentially a base, from what I understand. And this is just going to go ahead and change that BR to an OH. Then the other option is if you need to change it into an NH2, then you just do NH3. So this is getting really confusing because last unit we were doing a lot of this kind of stuff as well. And so that's why it's really important to keep the exam 3 material and the final material very, very clear. And it becomes tough on the exam. So again, like if you're looking at a problem and you see that there ends up being an OH or an NH2 in an alpha position to a ketone, that's a good sign that you first need to do alpha halogenation, then convert that halogen either into an OH or an NH2. Okay. So then he talks about the conjugation in alpha beta unsaturated aldehydes and ketones. So um, if you have a double bond, you would prefer for the double bond, and this is something everyone knows instinctually, you would prefer for the double bond to be in this position rather than be, just a second, um, rather than be in this position. Why? Because it's double, single, double, right? And this is double, single, single, double. So this is not conjugated, right? And that equals stable. Okay. Okay. Haloform reaction. So for the haloform reaction, this is basically he's showing you how to change, how to first add a BR or like a alpha halogen. Um, oh wow, okay. We need to go back and talk about this first. Okay, wait, let me take 1 second to talk about 1,2 addition and 1,4 addition. So 1,2 addition is where you don't have, because we learned this in the last exam of last semester. So it might not be quite there for most of you. So last semester we learned about heat control of 1,2 addition and 1,4 addition. So when we talked about 1,2 addition, it was, for example, if you have a double bond here and you react this with HBr, what's going to happen is that the double bond is going to go grab the hydrogen, and the hydrogen is going to follow Markovnikov's rule. So it'll end up, the hydrogen will end up being on this side, and we have a positive charge on this side. And then what's going to happen is that Br is going to come and attack that positive charge. So what we end up with is we end up with a Br here, and the hydrogen is here. This is called 1,2 addition. Now, 1,4 addition happens when it's a little bit, I think this is with heat. And then when it's a little bit, or room temperature. For 1,4 addition, it's when it's a little bit, or no, sorry. This one is when it's cold. So 1,4 addition happens more in the heat, and this is just a review of what we did last time. So double bond grabs the hydrogen again, but something interesting here is that this positive charge is actually, oh, by the way, this happens in dienes, right? And diene means that it has 2 double bonds. So this other double bond will go and transfer to the middle to take care of that carbocation. And what that leads to is then we have double bond here, the hydrogen here, and we have a positive charge here. So then the Br will come and it will attack there. And that gives us, so that's where the word comes from. So this one is 1,4 addition. Because in this situation, you added the Br 1 carbon away from where the hydrogen was added, whereas this one is 4 carbons away from where the hydrogen was added. So that's 1,4 addition. But here, when he talks about 1,2 addition and 1,4 addition, he's talking about some other differences. It's not just temperature. It's also like the other things that are involved in the reaction. So he's saying that 1,2 addition is done most often with strong bases and strongly basic things. And 1,4 addition is done with weakly basic things in general. So if you don't remember, like obviously we don't have actual strong bases most of the time in organic chemistry, but there are certain things that are going to be considered more strongly basic than others. And so, and these are nucleophiles, by the way, like strongly basic nucleophiles and weakly basic nucleophiles. So an example of your strongly basic nucleophile is here. So, and what's a nucleophile, by the way? A nucleophile is I think of it as something that is going to be substituted, okay? Something that's going to be substituted onto something else. So the example of 1,2 addition is this. So we're taking this and we're reacting it with HC triple bond C MgBr. So this should scream to you strongly basic. Strongly basic nucleophile. That's also going to react THF or some other solvent like that, and then H2O or H3O plus. So all that's going to do is we're going to remove the hydrogen from here, and then the this portion here is just going to attack straight onto there. And so what that's going to give us is, and this is 1,2 addition, so there's no rearrangement involved. Actually, that's not at all how this one works. It doesn't remove a hydrogen. That wouldn't make any sense. Okay, so anyways, yes, so this one involves no rearrangement, basically. And that's really, in the end of the day, the definition of 1,2 addition, that there's no rearrangement, whereas 1,4 addition does have rearrangements. So going back to the 1,4 addition example, so in the 1,4 addition example, and let me just change it up so it's exactly the same so you can really see it. So when we have our 1,4 addition, what's going to happen is that and an example of a weakly basic nucleophile is I don't know if you guys remember this from before, but here it's like a phenol with CH2 and then SH. So SH is one of the strong. It's an indicator that it's a weakly basic nucleophile. That's just something to keep in mind. Reacting with OH minus and H2O. So what happens here is that we are going to get a rearrangement. So the there. Okay, so the first step that's going to happen is that your nucleophile is going to, and I'm just going to write NU, and obviously nucleophiles always have a negative charge, and it's going to attack here on the farther side of the bond. Okay, from the carbonyl. And then after that, so it's going to be attached now. It's going to be attached onto the molecule. So what we get is this. But obviously this breaks octet. So where is that double bond going to go? That double bond has gone to this position. So I'm going to erase that. That's not there. Where it is here. But even once it's here, this can't work. This carbonyl have gone up as well. So you see that here we have 3 steps that all triggered one another. So as soon as 1 happens, 2 is forced to happen. As soon as 2 happens, 3 is forced to happen, right? So what we end up with is this down below, an O. And this is an O minus, of course. So at this point, the lone pair, the double pair. And so remember those little arrows we would draw that would just be like this? That shows that the double bond becomes a lone pair because why? Because it's forced to by the lone pair of the oxygen wanting to go back down into a carbonyl again. So in this situation, this is the first step that happened and it triggered 2. All right. And obviously in this case, it's not allowed to, here in gray, it's not allowed to go like all the way onto here because that would break octet at this carbon again. So that's why it's forced to become a lone pair like that. And then on the other side, we don't even have a carbon, right? So it can't go this way either. So the only option is for it to become a lone pair like that. And then from there, this one's really good. I'm so sorry, guys. Um, from there, I'm just going to redraw what we have so far with those arrows. So this has become a carbonyl again, which is neutral. Then we have a lone pair here, which is negative. And we have our nucleophile still attached. And by the way, nucleophile, when I say nucleophile, I just mean this thing. I just don't want to draw out the whole situation. Okay, so then the lone pair is just going to take up a hydrogen, and that is probably going to come from our solution or something because it needs to get a hydrogen. So you can just take from water one of the hydrogens. And that's what we get. So this is neutral because there's a hydrogen there. So all that is to say that there was a rearrangement. Instead of it going straight to the alpha hydrogen, instead of it attacking straight onto the carbonyl, it went next to the carbonyl, to the alpha position of the carbonyl. Okay, so let me point those out in red. So I have the nucleophile in the first case in the 1,2 addition. In the 1,2 addition, it got attached right onto the carbonyl. In the 1,4 addition, it went rearranged and got attached onto the more alpha position, even though there was a double bond there. So I think that the yeah. And so he has some notes here, and he says that there's actually a faster attack when you're attacking at the actual. So this one is actually fast. That means this one is slower, but this one is more stable. So he said when you attack the beta carbon, it actually gives you a more stable product. So this is more unstable. So I think these are really important to remember, these definitions of our new understanding of 1,2 addition and 1,4 addition. They might come up on the exam. So is everything kind of clear? Kind of? That I know that one was like super complicated. I feel like you might have gotten this one on the quiz.
Yes.
Yeah, I'm so sorry about how like annoying that is though. But just look at the overall picture. I don't know if you'll be asked for a mechanism. You might, so I would probably just memorize it just in case. Yeah, for sure. Okay, so again, the difference is whether you have a weakly basic nucleophile or a strongly basic nucleophile. I know, Anthony, you want to leave right around now. So I'm just going to continue a little bit longer, get like a little look at the next part of the lecture, because I at least want to finish the material from April 20th. So I've just come to the end of the document, the first document of the notes that he gave. So now I'm just going on to the second one where he just gives some problems. So I'm going to look through that and see if there's anything that would be helpful to point out. Yeah, so I guess I already kind of hinted that this would happen. Sometimes he'll give you a some kind of problem where you have to figure out what it came from originally. And so when you look at this, this is this would have to be, and this is using, he says, NaOH and heat. So this is telling me that it came from something that was probably broken right here. You have to figure out like what exactly it looked like. And so when you go back and look at it some more, you can assume that there might have been like an weight as well. Because this looks like it could have been like a I don't know, like an addition of like an aldehyde or something. So he says that this came from this. And then from there, it's kind of obvious that this was a carbonyl on its own too. So the two reactants were an aldehyde and a pentane-like ketone. And so, how does the mechanism for this work? Just to remind you of this, how this all works. NaOH, strong base. So strong base comes along with its negative charge, takes away a hydrogen, an alpha hydrogen. Alpha hydrogen attacks here. So alpha hydrogen goes, I'll label them with numbers. So it attacks the hydrogen, then that negative charge is goes up and attacks the carbonyl. Then this is forced to go up and become an OH. The OH is then protonated with the heat. So labeling all the steps, this is step 1. Step 2 is when the alpha carbon attacks the carbonyl. And then step 3 is where this goes up and it grabs an H from the surrounding thing. And then it gets, protonated after that. Or sorry, eliminated after that. So here's another one, just to practice as well. Okay, I think that's 1, 2, 3, 4, 5. So this one, you just have to figure out again, where did this come from? So as you know, all you have to do is remember that this probably came before it was the heat and the OH got removed. It was probably an OH like this, and then just cut it in half. And so the two products were whatever, this thing right here, and that was an aldehyde, and then also the other side of it, which was a ketone. All right. So it just goes on like that for a while. There's some cyclic ones, whatever. Actually, I think that's all from here. So let me just do a couple of retrosynthesis before we end for today, because it looks like the rest of that was just repetition, which is great. Make sure you go over it. So the first retrosynthesis problem, we have this primary alcohol, and it is associated with a benzene ring. And this is what we end up with. So what kind of thinking can we use to get here? First of all, when I'm looking at this, I'm seeing that it doesn't. So I think that this came from, and this is just, something that we already did multiple times. This came from this being a ketone. And then also possibly, I'm not sure about this double bond, but because if this was a ketone right here, that would be alpha addition, right? Onto this side. So I don't know, let's go back to the beginning. So from the beginning, we need to figure out a way to start attaching more carbons on. This right here cannot be, like, this is not going to be, and we can't do our alpha addition right away because there actually is no alpha hydrogen. So the first step is you could use, in the example, he uses PCC, PPC, no, PCC. And that'll just give you an aldehyde in that position. Once we have this aldehyde, there's still no alpha hydrogen that we could start substituting things onto. So the only way to add more hydrogens when you have a carbonyl, right, is through maybe like a Grignard, or actually more likely in this position is through a aldol condensation. Okay, so what does an aldol condensation use again? It uses two aldehydes or two ketones or something like that. So what kind of aldehyde should we use here? So if I look at my structure overall, so far I have everything up till here, right? I have all that. I need to add on 1, 2, 3 carbons only, okay? So I'm just going to go ahead and I'm going to do that. 1, 2, 3. And I know that I want there to be an alpha hydrogen on this one. So this one must have an alpha hydrogen on it because I want the alpha hydrogen to be the part that attacks the carbonyl. So if I put my alpha hydrogen here, right? Sorry, if I put my carbonyl here, the alpha hydrogen is here, and that's perfect because it creates this little shape where we now have this portion coming up on the side. And if you look at it closely, work it out, you'll see why this is necessary. And so this is the aldol condensation that we're going to do. So aldol condensation, we are going to form this into an OH, and then we get all of this. Okay. So this is what we end up with after the aldol condensation. From here, we only have to use maybe, I believe you can use H3O+, but here he uses heat. I think H0 plus would also eliminate it, obviously. So all that's going to do is it's going to take this and eliminate that OH. But we still haven't completely fixed everything. We need to change that carbonyl into an alcohol. And what's the best way to do that? The best way to do that is simply LAH or BH4. So LAH. That just gets a little hydrogen to attack the bottom of the carbonyl. So that's it for this retrosynthesis. So what I would recommend here is it's really important to pay attention to your carbons. If you saw where I simply counted the carbons here, and then I knew that this is what our product would look like, or that our reactant would look like. So that's some of the important steps to keep in mind here. Let's see if there's any other retrosynthesis. Okay, here's one more retrosynthesis that uses LDA, so I like that. So here we have a carbonyl that eventually cyclohexane, that in the end, it simply has an alkyl attached here, and that is so clearly just an alpha addition, right? But what are we going to add to the alpha position? So I think there's multiple ways to do this. The way he's doing it is not the way I would think of first. Let's do his way first, and then we'll see what I was thinking. I was thinking definitely to go more the route of what we've already talked about. I don't know. But anyways, so first he uses LDA, which what does LDA do? It just gets this ready for it's basically it helps something attack onto the alpha position. So he's using LDA with this structure. Now, is this structure necessary? Well, first of all, it kind of is really important that when we attach it on, we only want the addition of how many carbons? The addition of 1, 2 carbons. So if we attach it like this, those carbons can be 1, 2, that way. And so I don't really think that this one is actually so confusing. The alpha. This one is pretty confusing. I'm getting more and more confused, to be honest.
Fatima.
Mm-hmm.
Can I just not use LDA, THF, and CH3, CH2, Br?
Yeah, that's what I wanted to do. Yeah, I wanted to use more of a halogen based one. And this is really confusing me. Do you see how this could work even? Like, I'm honestly, like, super confused. Oh gosh. Okay, I see it now. Oh no, I don't. I don't see it. Um, oh yeah, I do see it. Never mind. Okay. Okay. So basically, I really think this is like really roundabout. This seems really crazy. Okay. So what he did is first he took um this that does is you're going to create an alpha hydrogen here because it's the only alpha hydrogen, so that's perfect. So this alpha hydrogen is removed and the negative charge will attack the carbonyl, right? And that would probably cut off, let's cut off the side to make it more like easier to see. So that gives us this. So from here, what's really interesting is that I think what he was trying to do is create an alpha carbon that's even like way stronger, right? Because at this point, this alpha carbon right here is the alpha hydrogen is pretty acidic because it's actually in between two carbonyls, so that's really cool. So from here, this is going to be OH and the BR. And so honestly, my idea was to just do this step first. I think that he was trying to strengthen the reaction here. And so from this point, it does exactly what you would expect it to. Just adds a BR here. One more. Oh, the BR is gone. Never mind. Okay, I'm completely brain dead at this point. But yeah, so this is your new alpha position, which is much more favorable, obviously. Then from this point, you just need to get rid of all of that. So the first step was to change it into an acid, and then from an acid, all you have to do is use heat to get it back. So the first step would be NaOH and H3O plus, and that gives us this reduced to an acid. So this is an OH here. Then it's just heat to get rid of it. So I honestly, when I'm looking at this problem, it probably could have been a lot easier. I think that the reason he did this is number one, to make this problem a lesson, right, about this portion right here. We need to remember the portion, and we need to remember that it's possible to do this. And secondly, this is going to be a way better reaction at the end of the day because we had a much stronger alpha acid or alpha hydrogen, much stronger acid of alpha hydrogen. So in general, this is just going to be a better reaction that's going to react faster, proceed faster, give us a bigger yield, all that kind of stuff. So I think that's it for today. We pretty much covered everything from April 20th, and that was a lot of material for sure, but it's going to be a little bit lighter on the 22nd and 27th. So the plans for continuing from here on out is that I think I'm going to have another review tomorrow, Friday, and then a final review on Sunday. So tomorrow, what we're going to do is we're going to work on a little bit more of the newer materials, and then Sunday will be a Q&A. And as for exam 3, which we didn't get to review, I personally think we'll be okay because there is a review session of exam 3 up on YouTube already from when we actually did it. So I think we should be okay in that area. And then obviously, if you have any questions, it was done very recently as well. So I feel like, you guys might be a little bit better in that area. If you have any questions about it, you do have to bring those questions to me because I don't think I'm going to be going over exam 3. But we'll try to take tomorrow to finish up on the final material and then Sunday to do any questions that you guys have. All right. I think that's it for today. All right. Thank you for coming, Babarka. In the recording.